So in this video, we talk about replacement policy. So we know that replacement policy that we to depend upon on the locality that we try to optimize. Usually that we are interested in the temporal locality. The first scheme or the first policy for replacement that the least recently used LRU algorithm that keep track of the last time that a block will access and evict from the block that have been unused for the longest period of time. So that's very simple, but the disadvantage of this approach is that it's complexity. So basically LRU have to maintain an access history of each block and which ultimately slow down the processing capability of the cache. The other scheme also very popular. That's the first in first out. We call FIFO. This in this replacement policy, the first blocks that have been in the cache or the longest have been in the cache for the longest time, regardless of when it will last year, will be replaced. On the other hand, the random replacement policy that what its name implies, so basically it picks a block at random and replace it with a new block. So the random replacement can certainly evict a block that will be needed often or needed soon. So, but it never traces. Definitely random replacement is very simple algorithm too, but it's not optimal. The performance of a hierarchical memory is measured by its effective access time, EAT. So basically, EAT is a weighted average that takes into account the hit ratio, the relative access time of a successive level of memory. So basically, the equation to compute EAT for two-level memory is given by this equation: EAT equal to H time access C plus 1 minus 8 times access mm. Okay, so basically 8 is the cache hit ratio, cache hit rate, and the access C and access mm, that's the access time for the cache and the main memory respectively. Okay. Here's an example of how to compute the EAT for different systems. Consider a system with a main memory access time of 200 nanoseconds, supported by a cache having of 10 nanosecond access time and a hit rate of a 99%. Okay, so that most of the time you can find information in the cache. Okay. So suppose we access to the cache and the main memory occur concurrently. Okay, so all we can do it all at the same time. So this one it means we can access overlap. Okay. So if that's the case, the EAT can be computed by 0.99. So that's the hit ratio right here, time with the access time of the cache. So 10 nanosecond right there. Plus with 1 minus 199, so 0.01. That time with the memory access time, that's 200 nanoseconds. So we can end up with the EAT equal to 11 nanoseconds. Okay. However, if the system doesn't allow we to simultaneously access both of the memory and the cache. So in this case, we do not have the overlap. So in this case, the EAT is computed by 0.99 time with the 10 nanoseconds. So in this case, if you can access the information in the cache, if not, you can take time to access the cache, because then we go there and we cannot find, then we gonna go to the memory and we find the information in the memory. So that's take longer time. So basically we have the 0.99 times 10 nanosecond plus 0.1 time with 10 plus 200. Okay, so this equal to 12 nanoseconds. So basically this system require a longer time in order to obtain some information. This equation for determining the effective access time can be extended to any number of memory levels. Okay, and as we can see later on the some other video in a different lecture. Okay. Also, the caching depend upon the program exhibiting good locality. So some of the objective-oriented programming have the poor locality owing to their complex and dynamic structure. For example, array stored in a column measure rather than row measure order can be problematic for certain cache organizations as well. So with the poor locality, caching actually cause the performance degradation rather than performance improvement, as we have been discussed so far. Also, where for the cache replacement policy, we also need to take into account the dirty blocks. So the dirty block is the blocks that have been updated while they were in the cache. Okay, dirty block must be written back to the memory. So a write policy determine how this will be done. There are basic two types of write policy: the write through and write back. The write through basically updates the cache and the main memory simultaneously on every write. On the other hand, the write back also we call the copyback, update memory only when the block is selected for replacement. Okay, so that we can form the two way to perform the write through and write back. We can see that the disadvantage of write through is that the main memory must be updated with each of the cache write, and definitely this scheme will slow down the access time on update. However, this slowdown is usually negligible, and the reason is that the most of the accesses tend to be read instead of write, so that's not a significant reduce the performance. On the other hand, in the write back, we have a advantage is that the memory traffic is minimized, but also have a disadvantage that the main memory does not always agree with the value of the cache. So that's gonna may cause a problem in the system with many concurrent users. So the cache we have been discussing so far is called a unified or integrated cache, where both of the instruction and the data are cached. However, in many modern systems employ separate cache for data and instruction. For example, that system we call a Harvard cache. So the separation of data from the instruction provide a much better locality, and the cost is that have a higher complexity. So simply making the cache larger provide about the same performance improvement without the complexity. So that's one of the things we should keep in mind. The cache performance can also be improved by adding a small associative cache to hold a block that have been evicted from the recently. For example, that scheme that block we call a victim victim cache. So a chase cache is a variant of an instruction cache that holds decoded instruction for program branches. Given the illusion that non-contiguous instructions are really contiguous, so that the concept of the chase cache. Most of today's small systems employ a multi-level cache hierarchy. actually, the level of cache form their own small memory hierarchy. So, for example, the level 1 cache usually have the capacity of 8 kilobyte to 64 kilobyte, and usually situated on the processor itself. And the level 1 cache have a much smaller access time, around a 4 nanosecond. The level 2 cache have a larger memory storage, that's a 64 kilobyte to 2 megabytes. So basically this one usually be on the motherboard and or an expansion card. The access time of the level 2 cache around a 15 to 20 nanoseconds. So this much larger compared with the level 1 cache in terms of the access time. In some systems that also employ the 3-level cache, so the level 2 cache is going to be placed on the same die as the CPU. By doing that, going to reduce the access time to between from the CPU to the L2 cache. So that's going to reduce the access time about 10 nanoseconds. And the level 3 cache basically have the much larger capacity, about 2 megabytes to 256 megabytes. That's referred to the cache that is situated between the processor and the main memory. So one of the number of cache level is determine the next thing to consider is that whether data or the instruction can exist more than one cache level or not. Okay, so we're going to discuss further in the next lectures.